So hopefully you find this kind of interesting, because for everybody this would be something new. So this section is about how we can use the dot product to figure out some fairly complicated things. Now, the dot product, which makes up about half of the problems on the assignment, is pretty darn easy to figure out, okay? So we're just going to click through and read here, and I'm going to add a couple of things to what the author has said here. So the dot product of two vectors. So it says you've studied two vector operations, vector addition and vector multiplication by a scalar. Okay, so multiplying a vector by a scalar, each of which yields another vector. So if we add two vectors together or we multiply a vector by a scalar, we get another vector. Okay, so the answer is a vector. Okay, in this section we're going to talk about something called a dot product. And when we find a dot product of two vectors, we actually get a scalar, which is kind of weird. You can multiply two things that have a direction and a magnitude, and what you get is a scalar. And a scalar only has a magnitude, it doesn't have a direction. Okay, so this is the definition of how you find the dot product. So if you've got vector u, which is u1, u2, so horizontal and vertical components here, vector v, which is v1 and v2, so the vertical components there. If you want to find the dot product, what you do is you take the two horizontal components, the first two components, multiply those together. Take the second two components, multiply those together, and then you just add the result. So this is going to be two numbers that are multiplied together. That's going to be two numbers that are multiplied together. And then you're going to add the result. Okay? And that's called the dot product. So it's a really easy thing to find. Okay, I'd like you to write something else here. Okay, I'd like you to write down what the dot product is, or what I would consider it to be. It is a scalar that contains information about the magnitude and direction of the two vectors. Now, it's true it's just a scalar. And this isn't a technical definition of what the dot product is, but that is in fact what the dot product contains. It's got information about it, about the two original vectors. It seems weird that one single number can contain information like that, but it does. And we're going to run into something when we start covering matrices that does something similar. It's called a determinant. Oh, did I hear a groan there? All right then. Okay. So let's talk about some of the properties of a dot product. Okay. And each one of these are going to be used at some point here, I think. So if I've got three different vectors in the plane or in space, now we just use two-dimensional vectors. If you take calculus 2, you're going to do three-dimensional vectors, which actually get pretty interesting. So the dot product is commutative. And if you think about how this is defined, it doesn't matter whether we do this one first and that one second. It's still going to be the first two components multiplied together, second two components multiplied together, and then added together. So the dot product is commutative. If I take the 0 vector and dot it with a vector, I end up with 0. Okay? If I've got the dot product of a vector and then dot that with the sum of two other vectors, I can get the same scalar by distributing that dot product through there. So I could do u dot v, and then I could add it to u dot w. And that's how we say the dot product. Okay, so we'd say u dot v and u dot w. Okay, if I find the dot product of a vector with itself, I end up with the magnitude squared. Now let's stop and think about why that would be. So if I had a copy of vector v, and I found v dot v, I'd take the two of those and multiply them together. So that would be v1 times v1, or v1 squared. And then v2 times v2, or that would be v2 squared. And that is the same as how we found the magnitude, and then square that. That's all it is. So if you dot a vector with itself, you end up with the magnitude squared. Okay, and that's going to come up again. And then if I've got a scalar multiplied by the dot product of u and v, I can it's not distributing through because you're just multiplying it by one of them. I can either multiply that scalar by w and then dot it with v, or multiply it with v and then dot it with w, and I get the same answer. Okay? So hopefully those kind of make sense. Let's go ahead and find a dot product now. Okay? So I'm gonna move this down here so we can't see what the answer is. I mean, it's literally this simple. The dot product of the two of these is going to be 4 times 2, which is 8. 5 times 3, which is 15. So I add those together. I get 23. There's a dot product. What does the dot product do for us? Remember, it contains information about both of these vectors, how long they were and which direction they were headed. Okay? So if I find the dot product here, multiply these together, that's going to be 2. Multiply these together, I get -2, so my dot product is 0. And on this one, I get 0 minus 6, so the dot product is -6. Okay? Dot products are pretty easy, right? Okay, so that just confirms the answer. Okay, and then it says, in example 1, be sure you see that the dot product of two vectors is a scalar. It's a real number, not a vector. Okay? And notice the dot product can be positive, negative, or 0. Okay? It's whatever that multiplication and then addition turn out to be. Okay, so let's take a look at this one. It says use the properties to figure these out. So if I were doing the dot product of u and v and then multiplying it by w, okay, think about this for just a second. This is a dot product. So this is going to be a scalar. Multiply it with the vector w. Is the answer going to be a scalar or a vector? I take a number and multiply it by a vector. Do I get a scalar or do I get a vector? I hear some whispers. You get a vector, okay? And what if I do a scalar multiplication with v, so I've got a vector, and dot it with another vector? Dot products always turn out to be scalars, so this is going to be just a number, okay? So this is going to be a vector for the result, and this is going to be a number for the result. So if I dot the two of these, find the dot product of u and v, that's -14. So I'm going to take -14 and I'm going to multiply it by the vector w. So that's just kind of like distributing, so I end up with -14 comma -28. Is that all right? There's the vector we were talking about. Okay, now they said use properties, and this can make things pretty easy. So instead of doubling v and then finding the dot product, if you already found the dot product, what I can do is I can kind of slide that out front and just say, hey, if I multiplied one of the vectors by 2, it's going to multiply the dot product by 2 because it changed the magnitude of one of those by a factor of 2. So we end up with just 2 times -14, and we end up with -28. Now, could I do -1, 3 and dot it with, let's see, 2 times this would be 4, -8. Could I find the dot product of that and end up with -28? I could do it that way if I wanted to. It said use the properties, and that can make it a little bit easier. Okay, but you could do it this way if you wanted to. Any questions? Sure? Okay. So the next one, I want you to read this one right here, and I want you to think about why that's true. You've got the properties on that same page. It's right at the top in that gray box. So it says the dot product of u with itself is 5. What is the magnitude of that original vector u? And it says it's radical 5. So why is that again? Yeah, it's that formula that says if you dot it with itself, okay, and they showed the work for it, if you dot it with itself, you end up with the magnitude squared. So if they're telling us if you dot it with itself, I end up with 5, they're saying the magnitude squared is 5. So if you want to know what the original magnitude was, just take the square root of that, we get the square root of 5. So the magnitude of u squared is 5. That's what they're saying, because they said the dot product of u with itself. So u dot u is equal to that, and that's equal to 5. So take the square root of both sides. So we get that the magnitude of u would have had to have been radical 5. Okay? Any questions? Okay. So you have a bunch of problems where they ask you to find the dot product, okay, or apply the properties of dot products. And then they ask you to do some problems that are a little bit more complicated, not much, okay? They ask you to find the angle between two vectors, okay? Now, I'm not going to derive this. They do derive this at the back of the book if you want to watch this. You can also find math nerds on YouTube that have shown how this formula comes about. But it says if theta is the angle between two non-zero vectors u and v, then the cosine of that angle equals the dot product over the product of the magnitudes. This is the dot product of the two vectors. These are the two magnitudes just multiplied together, okay? Or I like to write it like this, and I would like you to write it like this. The angle between the two vectors is the cosine inverse of the dot product over the product of the magnitudes. And when I use this formula, so I have most of these formulas memorized. When I use this formula, I remember learning this. I learned this, let's see, about 23 years ago in a linear algebra class at the University of Utah. Okay? And I always remember that phrase. It's the cosine inverse of the dot product over the product of the magnitudes. Cosine inverse, dot product over the product of the magnitudes. Okay? So if you can remember that, we very seldom use it in this form, although it is used in other formulas this way and to produce other things that way. Okay? But this is very useful for finding the angle between the two vectors. Both of those are good. If all you need to do is find the angle, just use the cosine inverse idea. Okay, are there any questions? Okay, this is going to come up again. Keep track of that one. All right? So the next one says, find the angle between these two vectors. Okay? So here's what we're going to do. We're going to say that the angle between those two vectors is the cosine inverse of, let's figure out what we put on top. What do we put on top? The dot product. So that's going to be 12 plus 15, so that's going to be 27 on the top. And then on the bottom, I'm going to have the product of two magnitudes. So let's figure out the magnitude of u. The magnitude of u is going to be the square root of, hopefully we're getting good at these, 16, 9, 25, so that one's 5. Magnitude of v, 9, 25. Put them together, I'd get the square root of 34. Can't really simplify that, so the product of the magnitudes is going to be 5 times radical 34. So in our calculator, we grab our calculator and we type in cosine inverse 27 over 5 radical 34. Do you need parentheses when you're putting that fraction in there? The answer to that is yes. Where do you need them? Yep. You need them around the bottom. Okay. That 5 radical 34 needs to appear in the bottom. Okay. There's the dot product over the product of the magnitudes, just like we have up here. And if you type that into your calculator, you get 22.2. Is that right? Okay. Doing okay so far? Okay. That took about 10 minutes or so to explain those ideas. Any questions about dot products, their properties, or how you find the angle between two vectors? Sure? Okay. Okay. We're going to look at this next part really carefully. I don't think I copied this off, did I? No, I don't think I did. So I want you to take a look at this, okay? And we're going to read through this. And I want you to think about this carefully, because if you can make sense of this idea, the rest of this they're relatively easy number problems, okay? And the other, they're embedded in story problems. The numbers on the rest of these problems are relatively easy to work with. It's the idea that's really important and the thinking skill that comes with figuring out My gosh, how would somebody figure something like this out? Okay? All right. So let's take a look at this one right here. It says, rewriting the expression for the angle between two vectors in the form this provides an alternate way of calculating the dot product. So instead of having the cosine of the angle be the dot product over the product of the magnitudes, if you multiplied both sides of that equation by the product of the magnitudes, it would cancel off the denominator here, and it would have the product of the magnitude of u times the magnitude of v in front of cosine theta. Is that okay? Just rearranging the formula, right? Okay. It says, from this form, because you can see that these are both magnitudes, and magnitudes are always positive, this side right here, oops, because that's always a positive, it says u dot v and cosine theta will always have the same sign. So let's think about that for a second. What they're saying there is that u dot v and cosine theta will always have the same sign. Why is that true? Or maybe a better question, what does that mean in layman's terms? I mean, it's a very short sentence, but what does that mean? If they both have the same sign, it means what? They're both positive or both negative. Okay, so they're either both positive or both negative. Okay, or I suppose it could be zero. Okay, they both have to be zero. Everybody good there? Does the logic of that little equation make sense in that sentence? Okay, so it says they'll always have the same sign, and it shows the 5 possible orientations of the two vectors. So remember, u and v are two vectors, and we can use the dot product to find the angle between the two vectors. So think about what happens right here. If this is the angle between the two of those vectors, and they are exactly in the opposite direction of each other, and that angle right here is 180 degrees, the cosine of 180 degrees is -1. So if this was -1, this would have to be negative. Their dot product would have to be negative. Is that right? Does that work? Okay. All right. Same thing here. If I have an obtuse angle, an angle between, they've got pi halves and pi, so that's between 90 and 180 degrees, the cosine is going to be negative. The cosine of that angle right there is going to be negative. So that means the dot product would have to be negative. What does this mean right here? Yeah. So if this is, if the angle between the two vectors is 90 degrees, the cosine of that would be 0, which means the dot product would have to be 0. So in these two cases, the dot product would have to be negative. In this case right here, the dot product would have to be 0, and guess what's going to happen right here? The dot product would have to be positive there, okay? So what we're mainly talking about is these 3 cases right here. It's either got to be 0, or it's got to be positive, or it's got to be negative. These are some unique cases right here where they're headed in exactly the same direction or exactly the opposite direction, and we're going to look and see how we can use that, okay? All right, any questions? So you'll notice that it's got a little statement down at the bottom. It says the definition of orthogonal vectors. Now, does anybody know what the word orthogonal means? It's what? It does sound like a disease. We have a couple of vectors that have a disease at this point. Okay. Well, we could go with that. The disease is called perpendicular. So if somebody says the word orthogonal, that is a fancy word for perpendicular. Okay? You could also use the word normal. Okay? Now, why would they make up a word like orthogonal for vectors? What did Mr. Perfect say?
I said because they hate us and they want to make our lives miserable.
They hate you and they want to make your lives miserable. It's very, very true. Yeah. That's why. So when we use the word perpendicular, we're usually talking about lines, right? If we're talking about vectors, we differentiate that just slightly and we use the word orthogonal, okay? So if we say we've got these things that are orthogonal, these things that we're talking about usually, they're going to be vectors, okay? Now, if you said the two lines are orthogonal, that still be correct? Yeah, but then you'd be showing that you hate the other person that you're talking to because you're trying to, okay? Make sense? Okay, and again, we also use the word normal, okay? So orthogonal and perpendicular mean essentially the same thing, so they meet at right angles, okay? So in order for them to meet at right angles, the dot product has to be 0, all right? So we're going to take a look at the next one, and it says, are these two vectors orthogonal? Well, you don't even need to check and find out what the angle is between them. Yes, it's asking, is the angle between the two of these 90 degrees? But if you want to check that, the only thing you need to check is the dot product 0? If it's 0, the answer is yes. What if it's positive? What if the dot product is positive? Tell me what that means again. The angle between them would be acute. What if it's negative? The angle between them would be obtuse. Okay? So in this particular case, when you find the dot product, you do end up with 0. That means those two vectors are orthogonal. That means they're perpendicular to each other. Okay? Any questions? Sure? Okay. We've got 5 minutes left. Here's what I'm going to do. Okay? I'm going to show you this formula right here, and we're just going to talk about why it might be true. Tomorrow I'll go through an explanation, and we'll do the last couple problems in this section, and hopefully give you some time to work on the assignment. So the next part of the section is about projections. It's about projecting a vector onto another vector. Okay? Sometimes we call it decomposing a vector or breaking a vector into its parts. Remember we did partial fraction decomposition? Okay, it's similar to that. Okay? Except we're taking a vector and we're breaking it down into two components. Okay? So if I've got this vector v and this vector u, and let's say, this one happens to be oriented so that this is horizontal right here. What I'm interested in doing is taking this component and figuring out how much of this vector u heads off in the direction of vector v. Whatever's left would head off in a direction that's perpendicular to that. Okay? So we're talking about projecting u onto v, and the notation that we use for that is this right here. We say projection of u onto v. Now don't get confused. It's not the projection of v onto u. Don't do it in the order that it comes to you. It's the projection of u onto v. Think of v being down a little bit lower, so u is on top of v. We're projecting u onto v. Okay, now let's take a look at this diagram right here. If I wanted to take however long u was and put a component that was in the same direction of v, how would I figure out how long this one is right here? Tell me a trig function that it would involve. So I want to take this length right here, and I want to figure out how much of that length goes in the direction of v. I'd use a cosine, wouldn't I? Okay? So I'd take the cosine of that angle, I'd multiply it by the magnitude of u, and that would be how long this is right here. Is that okay? Now, on this particular one, because of the way this is set up, it looks like v is horizontal, right? So this makes sense that that would be the horizontal component of that particular vector. You with me? Okay. But it's not necessarily horizontal. So take your paper and tilt it a little bit. What if it was heading off like this? So this is v and this is u. So it's not horizontal anymore. Couldn't you still draw a picture where we take this length and project it onto here and then figure out whatever's left? Does that make sense? So wouldn't I still use a cosine of that angle there? I would. Now here's all I need. This is how long it is. This is a scalar. That's how long it's going to be in that direction. What could I multiply it by so that it goes in the correct direction of v? A unit vector for v, right? Does anybody remember how to find a unit vector for any vector? You take the vector and you do something with it. Times by the reciprocal of the magnitude. So you figure out how long it is, and then you shrink it down to the correct size. So we found vectors last week that were 5 units in length. How did we make them 1 unit in length? Multiply them by 1/5. Or what I can do is I can take the vector v and I can divide it by its magnitude. Okay? Now, I'm going to take this right here tomorrow, and we're going to come up with that formula right there. If you can figure out how to go from here to there, that would be awesome. Okay? Because this is how you find the projection of u onto v. So if you can go from here to there, you're in great shape. You've got the thinking part of this figured out. And then tomorrow we'll just do a couple of other problems.